let's start. I'm very happy to be here. Actually, the last session of SDC. Unfortunately for me, I was traveling for most of the week, so I couldn't actually be at the conference. Just barely made it for now. But being at SDC and doing things with SNIA is always great fun and a lot of education. So I'm glad I was able to come now. And I'm going to talk about WekaIO. WekaIO is relatively new. We're several years old by now. A file system. We're actually the only file system written from scratch for NVMe over fabrics. So we're able to provide significantly faster performance. And because we have started from scratch, also significantly higher scale. So significantly more scale. So I'll just do a very quick build. So these are what we are doing. We're the fastest and the most scalable file system for AI and technical compute. Technical compute is the nice enterprise word for HPC. So some people see HPC and then they cringe. And we just call it technical compute and everyone's happy. We actually like HPC, but that's how it should use, and we strive to make sure applications never wait for data. So we want to build a storage system where if you want to add more compute and your application can parallelize, you're getting linearly more performance as you add compute. So that's what we're trying to do. And also, we're trying to make sure that when you are doing the new kind of workloads for machine learning, deep learning, when you have insane amount of small files, so when you think, for example, about a driving car, they have a number of cameras. Each vendor has different kind of cameras, taking pictures at 60 FPS, and then you have billions of quite small images because they don't need to be even megabytes. They're hundreds of K. And then you need the file system to sustain hundreds of petabytes of data of small files. So you need to have the kind of metadata services that actually scale to this kind of performance. Also, you need to make sure that all the operations that you run are low latency enough. So you can actually get high throughput for your applications because you need the gigabytes per second of that the 100 gig connections provide. Some of our customers, actually this is a small sample of them because most of them prefer not to be listed, and this is actually a smaller list than what's currently in the proceedings because we got requests to remove even more. So we'll go with them and make sure that the online version changes. We have some more exciting customers, but they are not willing to be there. But for AI, we have ZebraMed, which is running machine learning for radiology. Innoviz is running machine learning over their LiDAR imaging technology. TuSimple is running their fleet of autonomous trucks. iCarbon is running machine learning for medical records. AI Singapore is the Singapore machine learning project. We have some HPC workloads, Spookfish, Tree Altamira. Actually, we have San Diego Supercomputing Center. We have some more exciting HPC workloads that aren't listed. And very recently, Mellanox, that know us from a lot of the very interesting installations that we have started using us for their chip design. So we are actually the first, I think the first time ever a traditional large chip design company has switched to another file system that is not NetApp. And they've picked us instead of going with the new NetApp 9Ks for their chip design. And we're working on wrapping up results and coming up with very nice announcement around it. Partners, we have some folks from HP in the room. HP is actually reselling us. If you go to HP and you want to buy their machine learning storage, you're actually getting WekaIO, similar with Pinion Computing and Supermicro. We're very good friends with Mellanox. You need fast networking to have fast storage. There is no way around it. Similarly, we're friends with Intel and Micron because you need fast NVMe to have fast storage. NVIDIA makes the GPUs. We actually work with Western Digital mostly around their active archive because, as you'll see, we have the only parallel file system for NVMe over fabrics, but for tiering, for storing most of their capacity, we have implemented a traditional parallel file system algorithms like GPFS, Lustre, and Panasas, but instead of using SCSI and handling the hard drives themselves, we have created these parallel file system over S3. So we can tier natively to your on-premises object storage or to S3 on the actual AWS S3, which allowed us to let each customer use its own preferred way of aggregating hard drives. I didn't cheat and update the slides, but actually last week we also won the AI Conics Award. It's the most prestigious award in the AI space. I'm very proud of that one because we didn't put any money in pushing our solution, and I actually NetApp and Pure Storage did quite a lot of work to push their solutions, and we were the ones winning. So it was heartwarming. We got the Gartner Cool Vendor Award this year, and just recently, due to our numbers, we were listed on the 10 fastest growing storage companies, which is also great. Some customer quotes. We have quotes from DreamWorks that are using us for their animated videos. You probably have seen a video, a feature by DreamWorks. Too Simple is running their training for the autonomous trucks, San Diego Supercomputing, and actually we have a recent quote that I'm very proud of from Tri Altamira, and they have switched to using us on AWS, and they have switched to us in AWS instead of using the Intel Lustre distribution. And usually when we go for customers and we ask for quotes, we have a lot of quotes that talk about our performance, and actually Tri Altamira was talking about our stability and stellar support. So actually getting accolades from a customer that used to use a product from a large company about better support and better stability is great. So I will start by showing some graphs because we want to talk about performance, and after we see the graphs, we can actually talk about how we do it and why it makes sense. These graphs are actually, were all done in the HP AI lab in Houston, and they're all public on the internet. You have a very funny, the register article pointing to them, but if you just go to dlpg.lab@hp.com, you're going to see these numbers as well. So we did a few kind of tests. One test, we were running the same workloads that NetApp and Pure are publishing. And the reason we did it is because we needed to make graphs that have them both on the same scale. The problem with this graph is that both NetApp and Pure use benchmarks that are not I/O hungry. So there's very little story to tell around these graphs. But we can still see that for their workloads, we're slightly better than what they were able to do just with NFS. We did run all of their workloads and compared them to running off of local NVMe. There is some myth that a shared file system has very hard time being faster than the local NVMe. We break that myth. So instead of comparing to NetApp and Pure on the workload that they configured to not be very I/O hungry, we compare them to local NVMe, and we indeed proved that they're not I/O hungry because we received results that are very similar to the local NVMe. So the I/O system wasn't that much stressed. Then we went to run some workloads that the HPE guys found out to be a lot more stressful on the I/O. So some running ResNet 50 over the ImageNet with the inference mode. We know that customers actually see these issues also for training, but they use much bigger images than what you have in the ImageNet. So the way HP was able to do it and show good results with the public databases, it just run a slightly different kind of workload. And then when they did run all of them, they saw the biggest changes on the GoogleNet and the ResNet. And then they said, all right, so let's take ResNet, run it from a single client perspective, and compare 1, 2, 4, and 8 GPUs, and see how many images per second you can run. What you can see that for 1 and 2 GPUs, and then they compared to running off of DRAM, so the whole workload just fit in DRAM, no storage subsystem whatsoever. They were running off of WekaIO, and they were running on NVMe, and then they saw what result they would get. So 1 or 2 GPUs, local NVMe, DRAM, and WekaIO got the same results. 4 GPUs out of the 8 that you could use, the local NVMe was already maxed out, so you couldn't get results from your local NVMe, which is what usually people use for caching. And we were similarly good as running off of DRAM. And when with 8 GPUs, we were twice as fast as running from the local NVMe, and almost as fast as running from DRAM. Obviously, running from DRAM is not a real example because you have to load things in DRAM first. So computers don't put with all the data set into DRAM. And also DRAM's capacity is limited. So what we're showing that indeed, for these workloads, when running with GPUs, you do need a lot more throughput. And actually, NVIDIA is going to have GTCs soon. And you're going to see use cases and requirements that require significantly more throughput into than these numbers. And we're going to release a version next week that actually increases significantly the amount of throughput that we provide, basically by better parallelizing the PCIe transfers. Because when you run off of DRAM, you're moving the data from the DRAM through PCIe twice to the HBM memory of the GPUs. When you do it with WekaIO, you do it twice. You do it once from the network and then to the GPUs. And by using better parallelism of these PCIe transfers, we are able to reach much higher results that almost match DRAM. So you almost don't see any difference. Another benchmark we were running at a very prominent vehicle vendor that is going to have autonomous driving cars soon, that unfortunately I cannot use their name, compared to another prominent storage vendor with an orange color that I can also not mention their name, but you all know who is that vendor. I used that name once and then we got nasty letters, so I'm not going to do it anymore. But you probably can assume who that vendor is. And then they compared what happens for different kind of IOs that they run. So when they were running 1 meg IOs, which is actually easier IOs that they really have because their images are slightly smaller than 1 meg. The NFS-based all-flash filer got about 1 gigabyte per second, because this is what we see NFS usually provides. We were able to get 11 gigabytes per second for the EDR connection that they were using. Then, and this is actually what they needed for 4K. The orange all-flash filer was able to do about 60K IOs through NFS, and the latency was 670 microseconds. And we were doing 165. We could have actually done more 4K, but this is what their workload required. So they didn't pull more than 165. And the nice thing, when they compared to running this off of local drives, and run with the same queue depth. Obviously, queue depth 1, you get significantly lower latency, but fewer IOs. With this queue depth, the local file system provided the same amount of latency. Then that Orange company came back to that large customer and told them, hey, we understand distributed file system. They beat us for I/O. Try running metadata. So they had a file system with over 1 billion files, and they were running fine through it, just traversing all the files. What that Orange company didn't know, that was more than a year ago, on that bake-off, that we not only parallelize I/Os, we're the only parallel file system that also parallelize metadata. So that's the reason we can put billions of files in a directory and trillions of files in the namespace. So what took 6.5 hours on the monolithic all-flash filers actually took just 2 hours for us. So we were actually faster than a monolithic filer, which is another myth that customers have, that a distributed file system cannot be fast for metadata. And listing a large directory, we're almost 6 times faster than what they got with the monolithic all-flash filer. So we're showing that being able to parallelize I/O and metadata truly help achieving higher performance. We are also, this is spec SFS. The colors got screwed when I copied this file to the SNIA doc, but basically this line is a clustered NVMe flash cache NetApp system with 10 terabytes of NVRAM, so battery-backed RAM, so the whole workload fits in RAM. This is IBM GPFS v5 running over E8 NVMe over Fabrics block-based system. So it's already the v5 IBM over NVMe over Fabrics. What you can see is that the x-axis, we were able to get to 1,200 concurrent clients. This is just the benchmark numbers. You run the benchmark on several computers, and it finishes when it tells you how many concurrent clients it will run. You just tell him what number to try to get to. And this is an abstraction of clients that use and how the latency graph looks. So you want further out and lower. And what you can see that we were more than twice far out and significantly lower than IBM GPFS v5 and the biggest NetApp. So just a bit more introductory slide before I get to more details of why we do and how does it make sense. So what do you get with WekaIO? You're basically getting a shared file system that is fully POSIX compliant. So if you read the man page, we're going to do what the man page says. We also support NFS and SMB. So these are two protocols that are very popular that are not POSIX compliant. They're POSIX-like. And S3 and HDFS, so you can also run your key value applications at very low latency, and Hadoop. So you can actually use a lot of data based on the same platform. We run bare metal, like a lot of the technical compute or HPC users like, through or around the hypervisor. We integrate very well with Docker and Kubernetes, and we run either on your servers or in the AWS public cloud. So this is what you get. The protection, and obviously we're faster than the local file system. The protection is distributed coding based, so it's very efficient, and actually the bigger the cluster, the more protected you are because rebuilds finish faster. So we can show the model, and we let the clients put MTBF numbers, that the more nodes you have on your cluster, you actually end up being safer, and we're the only storage that can say that. We have scalable metadata, which is parallelized. So for example, and we can get back, just say it now, it's end of the later slides. Usually what happens for a file system when it looks at directories, there is a single node or a single CPU that is responsible for a directory. And then directories work well when they have hundreds of files, maybe thousands of files. They work okay if you have 1 million files, and then things start to go south. What we did, because we parallelize anything, any I/O goes to many different controllers where it runs lockless at very low latency, we have done the same thing also for directories. So basically what you see as a single POSIX directory is an aggregate of many seamless directory beans. Each directory bean holds just a few hundred files, so operations on that bean is very effective. The files end up being sent to a bean based on a cryptographic hash, so it's just safe, similar to what object storage solutions do. They just don't try to do it fast. And then all the operations that you do on directories, additions, removing, these kind of things, happen extremely quickly and in a lockless fashion of a single CPU that doesn't need to communicate with any other CPU. So additions and removal just talk to a single bean, and then we have a way to list directories to the POSIX protocol that will always get you the same results. So we have basically taken the POSIX requirement for directories and made sure that you can run as many directory operations as you want for huge directories where you keep the performance low. But now when you're listing a directory, you can actually find all these beans and run the list command concurrently in parallel, or when you're looking for things. So it allows us to actually leverage parallelism also for metadata. Directories is one example. Obviously, we're doing the same things for I/O. So each 1 meg of a file from the responsibility is actually being handled by a single CPU. And another thing we can do, we can move these responsibilities between CPUs extremely efficiently, so it can account for load balancing. So we show that we scale linearly even on AWS, and people ask how can it be possible. So we couldn't convince AWS to give us the instances without the noisy neighbors, but what we do when an instance is slightly weaker, it just serves less requests. And the instances that are stronger or they have more network throughput end up doing more work. We have the fast steering to S3. As I talked about it earlier, what we have done, we took the same kind of algorithms you would find for the hard drive-based parallel file system, the GPFS, the Lustre, the Panasas, and we've implemented them over S3. So if you have a large file, and now it needs to be pushed to S3, let's say you do it on a 1 meg chunk, if it's a terabyte-sized file, it actually happens as 1 million 1 meg put operations from all the nodes in the cluster. If your object storage scales, it's going to finish way quicker. Also, if one of these transactions takes slightly longer, the rest don't wait. When you're reading, hydrating from the object storage, the same thing happens. So we can actually leverage the high throughput nature of object storage, which is very difficult for customers to do because they cannot increase the queue depth. So we increase the queue depth that we work with the object storages transparently without the application having to be rewritten for it. We have also end-to-end data protection. So for each 4K that you write, we're actually storing a checksum on a different media. So unlike tit-and-diff, which makes a lot of sense because it's important to also keep the checksum for your data, but stores it on the same media. The problem with tit-and-diff, if a write didn't happen, but the previous write happened correctly and you're reading, the previous write that happens checks itself because the previous block was correct. For our system, if the write didn't happen, chances are that the write of the checksum to a different media did happen, it wouldn't check, and then we would use our coding scheme to recreate the block, rewrite it, and return the right data. So we provide the highest grade of data integrity. We support snapshots, clones. The snapshots are instantaneous to take. It doesn't matter how many nodes you have in the cluster. And when you take clones, you don't have any performance degradation. So when you start using the system, you have already taken a first clone. So on day one, you're running with snapshots. We have cloud bursting because we can take a snapshot and push it completely into the object storage in a manner that doesn't require the original cluster. So we actually have a lot of customers that want to run most of their workloads on premises, but sometimes need to spill to other places. They run on premises, they tier to the AWS S3, they take a snapshot, they push it to AWS S3. By the way, the next snapshot they will take, they only push the deltas, the differences. Now they can spin up an EC2 cluster. We scale linearly, so double the instances will get you double the performance. Double again, you'll get, again, double the performance. You can run this work on EC2, take a snapshot, push it to the same bucket. When you attach to that snapshot from the original cluster, it looks as if the work happened locally by just a clone split. So it looks the same as if someone took a clone, did the work locally, and just stopped working with the clone. Now you can just copy your data back. We don't do the merges because we are a coherent POSIX file system. We don't know how to do it, but you know your application, so when it's done, you can just do it, and we actually are integrating with some job managers that automatically talk to the cloud or talk to another data center. We have a large pharmaceutical company that unfortunately we cannot use the logo of, with the Boston and San Diego center, which they actually can push excess work from Boston to San Diego and get the results back. So it doesn't have to be with the AWS cloud, though this is the most prominent one. With security, we're using on-the-flight and at-rest encryption, and also we have authenticated hosts, so you can get the right kind of certifications that you may need for life sciences or genomics. We're using the Intel AES-NI, and we do it on the client, so there's very little performance degradation when we're actually running the encryption. Finally, we support IB or Ethernet, and we use dedicated, which means that you have servers that only do storage, though we can also run in a converged mode. When we run in the converged mode, you can have huge clusters running in converged. So this is the slide that usually gets the most controversy. So it takes some more explanation on what we do and why we do, and this explains how we're so much faster than a local file system. So the title here is Caching is Futile. So people used to think, hey, you cannot be faster than a local file system. The reason we can is that if you look at NVMe devices, and the logo doesn't matter because it boils down to physics, writing to a device takes about 30 microseconds. You may pay more and it will end at 25. You may pay less and it will end at 50. But this is about the same time, about the time it's going to take. Reading takes about 100 microseconds. If you have the right networking stack on EDR or 100 gig Ethernet, moving 4K page around takes a microsecond. So if you're running 4K IOs, then a local file system and WekaIO with 4K IOs takes about the same time because we have very little overhead for it. Now, what happens when you run bigger IOs? Most of your IOs are bigger than 4K. If you run 8K IOs, we can, actually what we do, we run 2 concurrent 4K IOs to 2 networked NVMe devices. So already at 4K, we're at better latency. If you run 64K IOs, and you protect 16 plus 2, we're actually going to run that IO as 16 concurrent 4K IOs that finish significantly faster than your local file system, even if you stripe over 4 or 5 devices. Now, if you run a meg, this is actually a great I/O. So people say, hey, for a meg, you can do for a hard drive. But what we do with the meg of an I/O, we actually run it concurrently 16 times as 64K I/Os, which at that point, the SSDs, the NVMe devices, kick into throughput mode. So we are getting the throughput number of the NVMe devices at very good latency. So instead of running a single 1 meg operation to your local NVMe device, which will actually be mostly serial, we run 16 concurrent 64K I/Os. So, and there is no configuration to do. So people ask us, what is your block size of the file system? The block size is 4K. This is the native size of the page cache. This is the native size of SSDs. You get the optimum parallelism based on the I/O that you run. You don't need to configure anything. So you will just automatically get the based parallelism based on the specific I/O that you're currently running. And that's the reason we can actually provide so much faster performance than a local file system. What use cases we're focusing on? We're looking for customers, and usually customers are looking for us. So AI, machine learning, or more recently, most of the GPU accelerated workloads require more I/Os than what the traditional storage subsystems provide and that traditional filers provide. So they're great use cases for us. Life sciences, imaging, radiology, all these use cases are great. Genomics is very, very strong use case for us. And then obviously the finance guys, the time series databases. We are partnering with KX. They're the maker of the KDB Plus time series database that all the financials like. Unfortunately, we cannot show financial logos. And risk analysis, or a lot of people use us for what used to be run on Fusion I/O. So people used to buy Fusion I/O devices, run a local file system or the Fusion I/O devices, get high performance. Now they cannot buy Fusion I/O anymore. They end up finding us, and then we give them a solution that gives them enough performance and in also shareable. So if you have tons of small files, a lot of metadata, if you care about latency, if you care about capacity, if your data grows and you don't want to keep paying for the old flash, and you're doing some sort of a local file system caching currently, this is probably something you should look at. This is actually a slide it didn't have for my talks, but then people told me I should add it because people just assume things. So we're actually breaking some of the shared file system myths that are out. So for the one, we've just broke that with the caching is futile slide. Local file system is faster than a shared file system. So we already broke it for I/O. We are now introducing what we call exclusive mount, which basically allows metadata operations to be cached in the page cache, dir entry cache, and attribute cache of the Linux. So actually running antar, for example, or git clone, or these kind of operations, when you run them on the local file system, they finish maybe 50 or hundreds times faster than on a shared file system. So for us, it will use the same kind of caching that the local file system does, so you're not going to get anything further from the local file system. But then we have our own tokens that we're using that are also scalable, unlike the other operating file system that use it for blocking. And we're integrating now the exclusive mount with leases, and then your local file system write cache, you can look at it, is going to be completely coherent. So as long as you're adding files to a directory that no one cares about, no other server accesses, you're getting a local file system performance because it doesn't matter. If another computer, another host would look up into that directory, it will then fall back down to the fully coherent mode. So you're basically not losing anything. So if you could run it in local mode, you'd use the page cache and the dir entry cache caching and the attribute cache caching. If it must be coherent, it will run in coherent mode. There is no configuration to be done. It will just work. File systems don't scale in capacity. Not a lot of things to explain, but we are exascale. The reason we're exascale is when we started WekaIO, it was obvious that you need to be that way. And file system don't scale in metadata, and you must use object storages to do it. We broke that myth because we're using our different kind of directories that parallelize. We did it for performance, but you also are getting scale out of it. So you can put lots of billions of files in a directory, and you can hold trillions of files in the namespace, and there is no problem. So really, you don't need to have either block storage to get higher performance, because we're faster than your block storage, and you don't need to hold object storage for scale. So what programmers like to do, they like to use the man pages and open files, close files, read and write to them. We let programmers just access the file system, and we solve all the problems that traditionally have plugged file systems. Usually I get a laugh after the next one, so hopefully you would help me. You don't need to have a PhD to operate a parallel file system. Didn't work. So this is something that we go and we replace a lot of these solutions. That's what we hear. All right, we can now go back to do our work. Because when you go in, replace Lustre, you do the other things, people didn't realize how much time they have spent appeasing the Lustre god, just making sure it continues running. We go into these places and we just make it run. Another reason we are faster is because we don't run on top of Linux. Linux has jitterness, and the jitterness in the Linux kernel is in many times longer than what you would want your IOs to take. What we have done, we're using Intel virtualization techniques to actually take away full cores, huge memory pages. We take direct link into the networking card. We support a lot of the Ethernet devices, obviously InfiniBand. On Amazon, we have full support for the ENA, so we run fully accelerated Amazon. And we have our own direct link to NVMe with our own NVMe stack. Also, i3 instances of Amazon are fully accelerated, fully supported. And then we do our own scheduling, our own memory management, our own networking stack that is compatible with TCP/IP. So you don't have to enable DCB or PFC. That's what FCOE required, which didn't get it to be accepted. And that's the reason we can also run on AWS. So we have our own networking stack, IO stack, scheduling, and memory management, which are geared toward low latency, high throughput, good utilization of your hardware. The only thing we do have running in the Linux kernel is actually our VFS driver. So we have implemented a Linux kernel VFS driver that implements all the interfaces that ext4 implements. So if your program runs on ext4 and you said, hey, I couldn't use NFS for it, it would run on WekaIO. The other thing we have, because we've realized people don't want to use our client everywhere, is also NFS and SMB front end, because you have legacy applications running on standard servers, and coming in Q4, also very low latency S3 and HDFS. So you can run your key value application. If you're currently running Memcached on a lot of servers out of RAM, we're going to get you similar kind of performance out of coherent NVMe. So we actually support them all. And another important thing, our client is enterprise grade. So for example, if you upgrade the storage cluster, the client realizes it automatically. So upgrades are obviously non-disruptive, they're hot. And when you have clients connected to that clusters, the client realizes the storage cluster is upgraded and upgrades itself. So the storage admins don't have to coordinate downtime with their users to upgrade the parallel file system. This is, I think, one of the biggest griefs of other parallel file system which have a client. So the client doesn't have all the downsides of the traditional clients. So I don't have a lot more time, and I want to leave some time for questions. So I have some more slides here that basically explain how we could run as dedicated servers. So this would explain the deployment. So you would have the dedicated servers, what you would call the storage appliance or RA, with NVMe and a lot of network connections. Then you can have your standard clients if you didn't want to upgrade to our clients anymore. And then you can have your CPU clients or GPU clients connected to them. Then we're tiering the colder data to S3 supporting object storage. Since there is no assumption for us where our compute actually runs, and we can either scale up or scale out, you can also run as converged. And you can have a converged storage cluster with a significant amount of servers into the many thousands. So now if Nutanix limits you to 50, and they call it a big cluster, you can run 5K or 50K nodes of converged when you have the storage, the NVMe devices that actually didn't, the colors are totally screwed, but here you have an NVMe device, and it runs over your IB or Ethernet network, and then you could still tier colder data to S3. This talks about why multi-protocol helps you, and also with tiering, I'm going to go through it. We said about the fully distributed snapshots. We talked about Snap to S3 helping with DR backup or cloud bursting functionality. This shows DR. So actually, if we're using cross-region replication in S3 with Snap to Object and at rest and in-flight encryption, WekaIO is going to be the easiest storage to get a HIPAA compliance. So you get your 3 copies and encryption very easy. Cloud bursting is similar. We've already discussed it. So you'd have your on-prem cluster tiering to AWS S3. You're taking a snapshot, pushing it to S3. Now you could start a different EC2 cluster, do some work while your on-premises cluster runs. You take a snapshot there, and you can view the results back on your on-premises cluster or another WekaIO cluster that runs in a different region. This is the security features I talked about. And another side effect that we also fix DevOps, Kubernetes, and Docker installations. So the thing about Docker, it assumes a local file system. And the containers get great performance when they run on a local file system locally. When containers are scheduled across 2 different servers, then Docker defaults down to NFS, and now performance plummets. And users are going to look for solutions. So I'll go through it because you understand it. Basically, what's going to happen here, you would just run Kubernetes on your CPU or your GPU clusters. And because you get faster than the local file system performance, when you run your Kubernetes and your Dockerized applications seamlessly, they would just scale to bigger clusters, and you don't have to care about scheduling containers to be on the same servers if they share data. And we also have a GUI, which a lot of people like. By the way, the GUI uses our public API, so you can either use the GUI or just script it. These are the features we discussed, and you can look at some feature comparisons to other platforms. So the Isilon, the FlashBlade, Lustre, and GPFS. These are usually what we see people use for technical compute, HPC, and machine learning environments. There is also NetApp, but they have most of the features. We have 5 more minutes, and now you can ask your questions. Maybe I was able to answer everything on the talk. Any questions? Obviously, no one has questions on the last session of the day. All right, so class dismissed.